Section 9.7b, this one, it should be up on Gradescope for you to be able to submit at the end of class. What we're talking about is approximations for Taylor polynomials. In other words, how good an approximation is our Taylor polynomial to the actual function at those specific values. So we're going to do three things. We're going to determine the error of approximating a function by a Taylor or Maclaurin polynomial. We're going to determine the degree of the Taylor or Maclaurin polynomial that we need for the maximal error value. And then we're going to say, given the degree, given the error, can we find an interval length about which that polynomial is a good approximation? So three different questions that we're looking at today. So where does this come from? The remainder of a Taylor polynomial, if you have your function, this part over here on this side is the Taylor polynomial. Now the Taylor polynomial only approximates the function, so this term right here is what we're going to call our error term. It's also called the remainder term, so that's our error or the remainder. It's difficult to find the exact error value. So we give a maximal error value. That's going to be much easier. And our maximal error value is going to be this right here. It's the next derivative from where you left off. Everything was power n. So it's the next term, essentially. That is what is going to be our error term, is our next term. And we don't know which value we have to plug in right here. This is actually going to be at some value. They call it an eta. It's a Greek letter. And it's at some value eta. But we don't know what that value is, and no one's figured it out. So what we do, instead of going through every possible value, which there's an infinite number of them, rather than going through every possible value, we just look at the maximum value that the derivative can have over the interval. And that interval is the value that we're approximating our function at to c. So it's either x to c or c to x. And you can determine your maximum value of your derivative on that interval. And that's what we're actually going to be looking at. So let's look at this example. It says a third Maclaurin polynomial for sine x is p3 of x, x minus x cubed over 3 factorial. This is a Maclaurin polynomial, so what does c equal to? 0. C equals 0 for Maclaurin. It says use Taylor's theorem to approximate sine of 0.1 by p3 of 0.1. So this is our x value, and our c is 0. So we're looking at the interval then, 0 to 0.1. That's the interval we're looking at maximizing it. So we have to find our next derivative. That is the value that we're looking at. And in fact, we're just going to put it in absolute value, and we're going to just maximize it on that interval. So let's find our maximum value. So the first things we have to look at is, if f of x equals sine x, what is f prime of x? Cosine x. What is the second derivative? Negative sine x. And what's the third derivative? Negative cosine x. And what is the fourth derivative? So we're back at the beginning. So this is going to be, I'm going to bound that sine x. So the maximum of the error, I'm going to look at that sine x over 4 factorial. But what is the maximum value of sine x? What's the maximum of sine? 1. And now find the maximum of our values of x on the interval 0 to 0.1, and what do you get? Yeah, 0.1. This isn't right over there, huh? There it goes. I thought it was going to update again like it did twice in 1 week. Come on, guys. So we just calculate this value. Any calculators? I suppose I could look at the book. So 1 over like that. So if you, what's 1 divided by 240,000? Five zeros. So a very small number. How about we just go with the 6 zeros and the 5 zeros and a 4? That work? Yeah, 5 zeros and a 4. Very small number. This is our error. This is the maximal error. Our error could actually be smaller than this. Notice we rounded up for the sine function. We rounded up for x. We used the biggest value for x in there. We made everything as big as it possibly could be and then called that our error. And we do that on our homework. Yeah. Any questions on that? You have a distraught look on your face. Got it? Question? Okay, in Taylor's theorem, it talks about an interval right here. That interval is x to c, or c to x, whichever, you have to put them in the right order. So that's where that's coming from. Okay, so let's look at another example. This one says determine the degree of the Taylor polynomial. So that first one went with the first type of problem. This is the second type of problem. Determine the degree of the Taylor polynomial Pn expanded about c equals to 1 that should be used to approximate natural log of 1.2 so that the error is less than 0.001. Here again, we're going to have our f of x to be equal to the natural log of x. Our c is 1, and we're looking at 1.2, so the interval is going to be 1 to 1.2. That is where we're going to be finding the maximum values for our derivatives. Now we start taking our derivatives. What's the derivative of natural log? 1 over x. What's the second derivative? Negative 1 over x squared. What's the third derivative? 2 over x cubed. What's the fourth derivative? And you guys are all wrong. Negative 3 factorial over x to the fourth. What's the fifth derivative? Positive 4 over x to the fifth. So what would the nth derivative be? Remember, we have to figure out a formula for the nth derivative. If you multiply those together, you can't do this stuff. Yeah, so n factorial x to the n plus 1. And then we have a minus 1 to a power. Notice when it's an even derivative, we get a negative sign. When it's an odd derivative, it's a plus sign. I would submit to you, we need an n plus first power. Oh yes. N minus 1 factorial, not n factorial. And x to the n. There we go. There's our formula for our derivatives. That is why I've been telling you, don't multiply anything out. Be lazy. Don't multiply anything out. Okay, so there's our derivative. Now what we have to do is we have to find our n plus first derivative. What would our n plus first derivative look like? Because remember, Rn is going to be the n plus first derivative. So how do I write the formula for n plus 1 here? Minus 1 to what power? N plus 2, which is the same as n, because we're just caring whether it's odd or even. So I can make that n, times n plus 1 minus 1 is what? N factorial over x to the n plus 1. There's my n plus first derivative. Now, let's look at this right here. I have to find the maximum value for this derivative on the interval 1 to 1.2. Where is the maximum value going to happen? Is it going to happen when you plug in 1.2? Or is it going to happen when you plug in 1? When you plug in 1, because you're dividing, you want to keep this number as small as possible in the denominator. So you need to plug in 1. So this value right here is going to be, oh, that's not going to work. Is going to be less than or equal to n factorial using x equals to 1. That's what I plugged in. So my remainder term is going to be going to have my derivative is an n factorial, and the minus 1 to a power goes away because that would only make it negative. I want the maximal value over n plus 1 factorial, and then times x minus c, c is 1, to the n plus 1. Now, what is n factorial over n plus 1 factorial? 1 over n plus 1. And what is the maximum value of x minus 1 to the n plus 1? What value should I plug in? 1.2 or 1? Yeah, 1.2 minus 1 gives you 0.2. And now I have made it as big as possible. So solve for n by setting this smaller than the error that we want. And the error I want is 0.001. How many of you guys have your graphing calculators with you? Okay, so go into your graphing display box. Then let me exit full screen mode, and I will show you what I'm talking about. You can do this in Excel or on a graphing calculator. When I'm using this as a stylus instead of as a computer, it's easier for me to do a graphing calculator than it is to use Excel. But you can do this in Excel. But what you're going to do is you're going to plug it into your calculator. You have your y equals button, and you're going to plug in your equation. So we had 0.2 to the, and I'm going to call it x plus 1. So x t theta n, just do x 1. I'm going to have to delete all that stuff there. And then I don't want all that extra. That was for a statistics equation. And then I'm going to divide that by my x plus 1. And if I've remembered my equation correctly, that is what we had. And we want this to be smaller than 0.001. So that is in our y equals. Now we can go to our table, which if you look right above the graph button on the top right-hand side of your calculator, it says table. So that's what we're going to do. Go to the table. And it has all these values of x. I've told it to increment it down by 1. That's the setting I have on my table. Where does this get smaller than 0.001? This is still bigger, but there is the smaller. So n equals 3. And that's how you're going to solve these questions. Does that make sense? What? With a graphing calculator, yes. Or Excel. On the test, you won't have this question. You won't have this question on the test. I won't give you something that a graphing calculator is necessary to solve on the test. A, I can't guarantee everyone has a graphing calculator. And B, I can't guarantee that you haven't put other things into your graphing calculator I don't want you to have. Question? Okay, so when that would have been n plus 2, but n plus 2 is the same thing as power n, because it's even or odd is all you care about. Yeah. Any other questions on that? Okay. Our n equals to 3 for our answer. Do you guys get to try one?
Is that bigger than our error? Or as long as they below our error?
Yeah, you're trying to say smaller than your error. You don't want it bigger than, you want it smaller than. Now that handout that I gave you should be what you can write your classwork problem on. The reason for that is because it is a PDF copy, and so then when it goes to scan it up onto Gradescope, it works better than just regular homework copy. So that's why I printed it out for you guys. But you guys are still going to keep this piece of paper with you. You can do any notes you want on that piece of paper. Paper comes supplied now. Yes, I can. I didn't even look. There we go. Up here. So this is what you're looking at right here. And you're going to choose your maximum derivative and then the maximum value for x. What makes this maximum value?
Where did the negative one come from down the bottom?
This one right here?
Yeah,
So you get a minus 1 over x squared, positive 2 over x cubed minus 3, positive 4, next will be negative. So you have to have an alternating sign, so minus 1 for power.
What happens to the L, or L, to the x1 of x on top, like,
Right here.
not there, okay.
So find your maximum value for this. On the interval 1 to 1.2, the maximum happens when x is 1. So that just leaves you an n factorial. Maximum means you throw away your minus sign, so just take a positive. So you just get an n factorial, and then that replaces this guy right here, that becomes your n factorial.
That's the same for everyone.
That's what?
Is that the same for everyone?
Well, however you do it, you find the maximum of that derivative on the interval, and then plug it in. So where's the derivative is e to the x. Your interval is 0 to 0.6. What is the maximum value of it? E to the 0.6. So you're going to plug in e to the 0.6 overhead plus 1 goes to the 0. We're on the what?
Check out.
of your derivative right here on the integral. Your integral is 0 to 0.6, right? Yes. So look at your derivative. It's e to the x, right? What is its maximum value on the integral 0 to 0.6? E to the 0.6. And so you plug that in for that right there. So go ahead and write that down. For just this f of to the n plus 1 of x. Just say, no, that's an x. Yeah. So that becomes your e to the 0.6 right there. No, you don't have times the x. You just have the e to the 0.6. Where I have an n factorial, you have an e to the 0.6. This part you just copy down. That doesn't change. And then you have to look at x and c. C is 0 because it's before. X is anything in the interval 0 to 0.6. Where is that going to be the biggest value? When will this be the biggest? At 0 or at 0.6? 0.6. Yeah. If you want this to be the biggest number, 0.6 is bigger than 0. So this whole thing becomes our 0.6. So you're going to have 0.6. You'll have e to the 0.6, and you have n plus 1 factorial. And then you're going to make that all smaller than the error that I asked you for on the paper. Plug it into the calculator.
So when you get there,
Plug it into the calculator. Yeah. Or Excel. You can't go any further than that.
so you don't want to
I was born in Africa in Senegal, and I lived there for about a couple of years, did stuff for about 5 years, and 4 years. Michigan for Maryland for 5 years, Texas for 10 years.
So the better question is where.
Which my translation is. When I get tired, it's very Texas small. Really? I was. Yeah.
You work the word
so
And when I'm energized, I talk quite fast. So that comes from when I ever listen to an Indian from talk about it. So that comes from.
every single one. So maximum is just e to the power.
I'm thinking like
As almost done, just left us for yeah, that thing, that's that thing. So, what this is, let's say, e to the power is 0.6, equal to n plus 1 and 1. 0.6
We're gonna solve for n. So that this whole thing is less straightforward. You have to get to the 6 over n plus 1 factorial.
Slide slow. That higher.
That comes from your
So basically you graph. This is the web. Yeah. They get down to what is it?
Yeah, you can do that. I think it's like
So they have to
yeah, if you can't get it into the calculator, it should work. These calculators actually allow us to like to get it. If you look at this right here, you can go to the math. There's your factorial notation, but Okay, so this one, find the maximum. And then this one, find max. Yeah, you're just going to plug in your exponent. Notice the exponent came down. Yeah.
Yeah, like the fact that
Okay, you guys should be getting n is equal to 5 on this one, I believe.
Yeah, that's on grade 2. Grade 2, it's on grade 2.
Yeah, we're going to put that on grade school. Okay, do we all have this one done? We have one more example to do for your homework. And I have 9 minutes to do it and 8 minutes to do it and now. So we're going to assume you're done. N equals to 5 is the answer. If you do not have a calculator, that'll do it. N equals 5 is what I'm looking for. Okay, so the last one, determine the values of x for which the function can be replaced by the Taylor polynomial if the error cannot exceed 0.001. Here again, I'm looking for, wrong color, I'm looking for my remainder term. And this is our n plus 1 derivative over n plus 1 factorial, x minus c to the n plus 1. And we are told that the error is 0.001. Notice they give you to the 5th here. So this is a 5th degree polynomial right here. I'm going to put this up here. N equals to 5. So that's the 5th degree. So I need to check for n for the 6th derivative. I have to check the next derivative. Do you guys see that? N equals 5 says check the 6th derivative. So here again, f of x is equal to sine x. They tell us that right there. So what's the derivative of sine x? Cosine x. What's the second derivative? Negative sine x. Third derivative. Oh, I forgot the negative. Negative cosine x. The fourth derivative? Sine x. The 5th derivative? And the 6th derivative. Now, I need to find the maximal value of the negative sine x. I can either take it on the interval that they give me, but I don't have an interval, or I can use the maximal value of sine x. What is the maximum value of sine x? 1. So I'm going to use 1 for it. So we're going to have 1 over n plus 1 factorial in the denominator, and then the x minus c to the n plus 1. Notice I left that in absolute value. So what we want to do then is to solve the equation 1 over n plus 1, except what is n, guys? 5. What is 5 plus 1? 6. So I can write this as 1 over 6 factorial. I'm going to solve this. 1 over 6 factorial. X minus c to the 6th. I want that less than 0.001. So I'm going to multiply by my 6 factorial on both sides. And what I get then is x minus c. By the way, is c 0 or 1 or a non-zero value? What is it? They haven't subtracted anything from those x's. So c is 0. Even though they said a Taylor polynomial, remember a Maclaurin polynomial is a Taylor polynomial with c equals to 0. So if they had said x minus 1, then I know c is 1. But they didn't, so I know c is 0. So I can write this as x to the 6th is less than 6 factorial times 0.001. Take the 6th root of both sides. And then take it outside of the absolute value. So minus the 6th root of 6 factorial times 0.001 is less than x is less than the 6th root of 6 factorial 0.001. That's your answer. This is the type of test question you are going to get.